Assalamu alaikum and a warm welcome to all of you. In earlier videos, I discussed the zero sum game and the prisoner dilemma. In this particular video, I'm going to explain the Nash equilibrium and the dominant strategies in the game theory. So, let me start with a basic introduction to the equilibrium in the market. According to the theory of demand and supply, the notion of a market equilibrium in which demand equals supply is central. Given the equilibrium price and quantity, no market participant, that is the buyer or the seller, has any incentive to change their behavior because the market is in equilibrium and the equilibrium price and quantity have been determined. In the strategic setting of the game theory, we will adapt a related notion of equilibrium formalized by John Nash in the 1950s called Nash equilibrium. And Nash equilibrium is one of the most important concepts in the theory of game. Nash equilibrium involves strategic choices that once made provide no incentive for the players to change their behavior. And it is a strategy for each player that is the best choice for each player given the other's equilibrium strategies. The theoretical attraction of the concept arises because in such a situation there is no tendency for anyone's behavior to be changed. Now we will define it in a formal way. Nash equilibrium can be defined simply in terms of the best responses. In an n-player game, strategy SI is the best response of the ith player to rivals' strategies shown by S sub negative I. If player I cannot obtain a strictly higher payoffs with any such possible strategy, SI, that is a particular course of action, is in the possibility sets given that rivals are playing S sub minus I. Best response. SI is the best response for the player I to rivals strategies. S sub minus I denoted SI is included in best response for I in other possible strategies. If the utility of the ith player from SI and S minus I is greater than or equal to UI, that is the utility of the ith player, Si prime, S minus I for all Si prime belongs in the possibility set. There may be a set of best responses rather than a unique one. That is why we used the set inclusion notation. Si is a member of BRI, S minus I. There may be a tie for the best response, in which case the set BRI will contain more than one element. If there is not a tie, then there will be a single best response Si, and we can simply write Si is equal to BRI. We can now define the Nash equilibrium in an in-player game as follows. A Nash equilibrium is a strategy profile including S1 star, S2 star up to Sn star, such that for each player I, where I varies from 1 to n, Si star is the best response to the other player's equilibrium strategies S star sub minus I, that is Si star is included in the best response. Now we would like to discuss Nash equilibrium in the prisoner's dilemma case. Let us apply the concepts of best response and Nash equilibrium to the example of the prisoner's dilemma that we discussed earlier in case of the two suspects and there were two strategies. confess and not confess, or think and remain silent. Our educated guess was that both suspects will think or they will confess. We will show here that both confessing or thinking is a Nash equilibrium of the game. To do this, we need to show that thinking is a best response to the other player's thinking. Refer to the payoff matrix in the below figure. This is the payoff matrix that we have already discussed in the prisoner dilemma case. So if player 2 thinks, we are in the first column. If player 2 thinks, we are in the first column. If player 1 also thinks, his payoff is 1 and we are here. If he is silent, his payoff is 0, then we are here because he earns the most from thinking. Given player 2 thinks, thinking is player 1's best response to player 2's thinking. So when suspect 2 thinks, then suspect 1 will think because that is the best response. As in this case, his utility is equal to 1, but here his utility is equal to 0. So in case suspect 2 thinks, then suspect 1 will think also. Because players are symmetric, the same logic also implies that player 2's thinking is a best response to player 1's thinking. So it means that if both think, then both of them have best responses to each other's. Therefore, both thinking or both confessing is a Nash equilibrium. So this is a Nash equilibrium. We can show more that both thinking is the only Nash equilibrium. To do so, we need to rule out the other three outcomes. Consider the outcome in which player 1 thinks and player 2 is silent. So we abbreviate this as think silent. The first player or the suspect 1 confess and suspect 2 remain silent. So we are in the upper right corner of the matrix in the previous payoff matrix. This is not a Nash equilibrium. Why? Because given that a player 1 thinks, as we have already said, that player 2's best response will also be to think, not to be silent. And symmetrically, the outcome in which player 1 is silent and player 2 thinks in the lower left corner of the matrix is not a Nash equilibrium. That leaves the outcome in which both are silent. Given that player 2 is silent, we focus our attention on the second column of the matrix. The two rows in that column show that player 1's payoff is 2 from being silent and 3 from thinking. Therefore, silent is not a best response to think. Therefore, both being silent cannot be a Nash equilibrium. So the only Nash equilibrium is when both of them think. So if player 1 think, player 2 will not remain silent. If player 2 thinks, player 1 will not remain silent, and both will not also remain silent. So the only Nash equilibrium is that when both of them are thinking or when both of them are confessing. To rule out a Nash equilibrium, it is enough to find just one player who is not playing a best response and thus would want to deviate to some other strategy. Considering the outcome, think silent. Although player 1 would not deviate from this outcome as he earns 3, which is the most possible, player 2 would prefer to deviate from silent to think because being silent is not the best response. Symmetrically, considering the outcome silent think, although player 2 does not want to deviate, player 1 prefers to deviate from silent to think. So this is not a Nash equilibrium as well. Considering the outcome silent or not confess, both players prefer to deviate to another strategy, more than enough to rule out this outcome as a Nash equilibrium. So the outcome silent is also not a Nash equilibrium. So As we discussed, think or confess is a Nash equilibrium in the prisoner's dilemma case because thinking or confessing is the best response to the other player's thinking. Thinking is the best response to all other players' strategies. Think silent. This can be seen among other ways from the underlining procedure shown in the below figure. All player 1's payoffs are underlined in the row in which he plays think, and all players 2 payoffs are underlined in the column in which he plays think. A strategy that is a best response to any strategy the other players might choose is called a dominant strategy. Players do not always have dominant strategies, but when they do, there is a strong reason to believe they will play that way. Complicated strategic considerations do not matter when a player has a dominant strategy because what is best for that player is independent of what others are doing. So we now discuss a dominant strategy, which is a strategy SI star for player I that is a best response to all strategies profile of other players. That is, SI stars is included in best response to all strategies profiles of the other players for all S sub minus I. Now we may note the difference between a Nash equilibrium strategy and a dominant strategy. A strategy that is part of a Nash equilibrium need only be a best response to one strategy profile of other players, namely their equilibrium strategies. A dominant strategy must be a best response not just to the Nash equilibrium strategies of other players, but to all the strategies of those players. If all players in a game have a dominant strategy, then we say the game has a dominant strategy equilibrium. As well as being the Nash equilibrium of the prisoner dilemma, think is a dominant strategy equilibrium. It is generally true for all the games that a dominant strategy equilibrium, if it exists, is also a Nash equilibrium and is the unique such equilibrium. Ladies and gentlemen, I hope this was interesting for you. We discussed the Nash equilibrium and the best response as the dominant strategy. Kindly subscribe the channel if you haven't yet subscribed, and don't forget to click on the bell icon so that you can be informed by notification that when I upload new videos for you. Thanks for watching this video. Kindly subscribe this channel and share various videos of this channel with your friends, with your colleagues, and with